Today we're going to learn the different types of chemical reactions. There are 5 basic types, and that will get us through most chemical reactions, at least that we'll see in this class. If we know these patterns, we can learn to predict the products, and that's really what we're working towards, on how can we predict what 2 reactants are going to make. So let's learn the patterns first. The first type is a synthesis reaction, and it takes this form: A plus B gives you C. Now, it could be A plus B plus D plus E plus F gives you C, as long as it's only forming one thing. The way I remember this one is synthesis. If I synthesize music, that means I'm making music. So in a synthesis reaction, we're making one thing. Here we can see it play out in a actual example. We have carbon monoxide plus oxygen gas, and that is going to produce carbon dioxide. That is a synthesis reaction because we only have one product. So on your look for statements in your notes page, I want you to fill in look for a single product, and that will help you identify a synthesis reaction. Another example that we got to see firsthand in our lab the other day was the oxidation of metals. We had a metal plus oxygen yields metal oxide. So we did magnesium, and we lit it on fire. So when we see O2 in a reaction, that means we're lighting something on fire, and we are going to get magnesium oxide. Magnesium's in group 2, so it's 2 plus. Oxygen is 2 negative. The sum of the oxidation numbers is 0, so you just have to write it down without any charges. And then, because yesterday we learned how to balance reactions, from here on out, it is your new obsession that every equation should be balanced. This equation that I have written here should bother you because it is not balanced. So anytime you see a reaction, make sure it balances. I have 2 oxygens in the reactant side. On the product side, I only have 1, so I'm going to put a 2 right here. That lets me know I have 2 magnesiums as well, so I need to put a 2 there to make it completely balanced. All right. Our next type of chemical reaction is a decomposition reaction, and it follows this form. C gives you A plus B. Now, it could be C gives you A plus D plus B plus E plus F. It doesn't matter how many pieces it breaks up into, it's just that it is one thing breaking up. Here's an actual example. Now, this one would, of course, have to have heat written over it, because these would have to be heated. And we've got mercury oxide, and when you heat it, it will break down into mercury and oxygen gas. And then we could then test for the oxygen by seeing if it supported combustion with those wooden splits, the glowing embers on the end of a wooden split. All right. So for our look for statement, what we're looking for to determine whether it is decomposition is 1 reactant. So decomposition, look for 1 reactant, and that'll let you know that. Common decomposition reaction is the breakdown of water to yield hydrogen gas and oxygen gas. So water, when you apply electricity, breaks down into hydrogen gas and oxygen gas. Those are both diatomic, so they have to be written as H2 or O2. And of course, it needs to be balanced always and forever. So if I put a 2 there to fix my oxygens, then I have 4 hydrogens on my reactant side, so I need to put a 2 there so that I have 4 on the product side as well. I think that's a very interesting reaction. I think the flip side of that is a little more interesting. So it's a synthesis reaction. Hydrogen gas plus O2. Remember what I said, when we add O2 to something, that usually means that we are setting it on fire. So if we set hydrogen gas on fire, we get water. Now, it probably is going to be water vapor, just because when we set things on fire, they tend to get pretty hot, and that is enough to separate the water molecules. But still, I think it's pretty interesting that you make water out of fire. Yeah. The third type is single replacement. Now, you might also see it in your book as displacement. Replacement, displacement, potato, potato. It's the same thing, so I don't want you to get hung up on the words there. So in single replacement, it has this form. A plus bx gives you ax plus b. And I'm going to teach this to you the same way that I learned it. So let's say a reaction is a dance. A is going by himself, and B is taking X. We'll say that X is the lady. After the dance, A's going home with X, and B's going home crying. So one metal is going to replace another one, or one halogen will replace another halogen. And we'll look more into that as we go a little bit further into chemistry. Here's an example reaction. You have aluminum plus zinc chloride is going to give you aluminum chloride plus zinc. So aluminum came in, and it'll always be metal replacing metal or halogen replacing halogen. Your two metals will both have positive charges, so they will not want to bond to one another. So aluminum is going to give zinc the boot, so it's our single element over here. And then aluminum is going to bond to chlorine to form aluminum chloride. Now, I want you to look. Here it's ZnCl2. Here it's AlCl3. The reason that it's Cl2 here is because that 2 came from the charge of zinc, and zinc's charge is 2+. The reason it's aluminum chloride here with a little 3 is because 3 is aluminum's charge when it is an ion, and we had to crisscross. So the subscripts on the bottom of the chlorides have to deal with what they are bonded with. So always go through your charges, crisscross to write your answers. Metals just by themselves, like aluminum and zinc here, they have no charge because they are just that metal. They are metallically bonded to other things. Other atoms of the same type. So as one atom switches, it bonds from one element to another. An easy characteristic to look for, so what I want you to look for is a single element on both sides. Single element on both sides. Now, beside that, I want you to write diatomics count as a single element. Because they can't get any more single than that, H2. You can't just have H. So H2 is a single element of hydrogen. Okay, fourth one is double replacement, or again, double displacement. Don't get hung up on the words. And it follows this form. AX plus BY gives you AY plus BX. Here, I want you to notice that A and B are in front on the reactant side. They're also in front on the product side. So those guys aren't going to switch. What happens is that the anions switch. So X and Y just switch partners. Here it is, an actual example, or a real example of that. And we have barium chloride plus sulfuric acid gives us barium sulfate and hydrochloric acid. Again, barium and hydrogen are our positive ions. They're going to be in front, always. And they just switch partners. Over here, barium is no longer bonded to chlorine, it is now bonded to sulfate. And hydrogen over here on the product side is no longer bonded to sulfate, but now it's bonded to chlorine. And again, we dealt with the charges to write those formulas correctly. So don't forget how to write the formulas correctly. So both atoms switch elements they bond with in this type of reaction. So it's best identified when you have compounds on both sides of the reaction. Basically, two compounds on each side of the reaction. So that's your look for statement in double replacement. Another type of reaction that is a subset of double replacement is acid-base neutralization. And here we have an acid plus a base yields always a water and a salt, not necessarily table salt. So if I have an acid, like hydrochloric acid, it's a pretty strong acid, and if you were to put your finger in a solution of concentrated hydrochloric acid, it would eat your finger off. And I react it with the base. All of our acids start with hydrogen. Our bases are most of the time going to contain hydroxide. Sodium hydroxide is a very strong base, and if you were to put your finger in a concentrated solution of that, it would turn your finger to soap rather painfully and quickly. But when they react, now I'm going to show you a strategy for completing double replacement reactions. And this is something that I'm going to ask you to do as we go through this chapter and the next, and actually from here on out. So pay attention. So what we're going to do is we're going to take the first things, our cations, and we're not going to write it in the same line as the arrow. We're going to write it kind of our scratch work up at the top. So I have H+, I write it as a charge, or as an ion, and Na+. And then we're just going to switch partners. Hydrogen will no longer be bonded to chlorine. It's now going to be bonded to hydroxide, and I write it up there with its charge. And sodium will no longer be bonded to hydroxide. It's going to be bonded to chlorine. And so HOH is H2O plus NaCl. And then you would check it for balance. So that's how you're going to complete reactions, at least double replacement reactions. All right, last but not least is combustion. Right? Combustion kind of screams setting things on fire. So we have a hydrocarbon. That's something that only has hydrogen and carbon in it. And we're going to add oxygen to it. That represents our fire in a chemical reaction. It is always, always, always going to give you carbon dioxide and water. So we have this example. We have methane here, and we're going to add oxygen to it. And when we burn methane, we get carbon dioxide and water. Now, methane is a fart. So this is the chemical equation for burning a fart. I don't recommend it. They will burn, but I don't recommend it. Usually the flames will follow the source of the fuel. And this water, it won't be liquid water. It is going to be water vapor, again, because we're burning something there. We could also have this, 3H8 plus O2. This is propane, as in a propane grill. And if we set it on fire, we're going to get carbon dioxide and water. And of course, you would balance that. This one here is going to be pretty easy. I have 3, and then I have 8 hydrogens on my reactant side. So I have to put a 4 there so that I have 8 on the product side. For my oxygens, I have 6 plus 4, that's 10. And so I have to put a 5 here, and now that equation is completely balanced. This is a butane lighter. If I light, oh, sorry, that should be a 0. If I light it on fire, I'm going to get carbon dioxide and water. So you should never, ever miss a equation that is combustion. It's always going to give you carbon dioxide and water, no matter what you're burning, whether it's a fart, butane, or propane, you are going to get carbon dioxide and water. This one's a little more tricky to balance. I have 4 carbons here, so I would start with a 4 there. And then I have 10 hydrogens on the reactant side, so I'll put a 5 there, so that I have 10 hydrogens on the product side. And then when I look at my oxygens, I have 8 plus 5. That gives me 13. 6.5 times 2 is 13. So when that happens, our strategy, because we can't keep that decimal around, is to multiply everything, all the coefficients, by 2. So it would be 2C4H10, and then here would be 13 oxygens, and here would be 8 carbons, and over here it would be 10 waters. And if you look at that, it comes out balanced every single time, so that's a handy strategy. Now, when you burn octane, which is also another hydrocarbon, and your car, it should produce carbon dioxide and water, but we're always worried about carbon monoxide when we're dealing with cars. And that's because our engines in our cars are not perfect. And so we end up having incomplete combustion, and that gives us carbon monoxide. And to make gasoline burning cars safer, the permitted CO in exhaust is regulated, and that is part of your inspection. If you have to be worried about carbon monoxide, especially if you use heat or wood for heat in the winter. You need to have a carbon monoxide detector. It is a deadly gas, and it's the kind where you fall asleep and you don't wake up.